All right, so we have the ratio test, which says that if the limit as n goes to infinity of the ratio of adjacent terms in a series is less than 1, then the series itself converges. And notice that it's the later term that's on top in this ratio and the earlier term that's on bottom. So let's look at an example of how we can use this. So let's look at this series, sum from n equals 1 to infinity of 2 to the n over n factorial. So hopefully it seems very unclear whether this should converge or not. But let's have a look. In fact, it's not even totally clear whether these individual terms go to 0. This actually is something that we looked at before, and the individual terms do go to 0, but that doesn't really tell us anything about whether the series itself converges. But let's use the ratio test, right? It's hard to know what other test we might use because this numerator is getting really big. It's hard to know exactly what this fraction is, so it's hard to compare this to some other series. It's definitely not a p series, so we can't use the p series test, right? Not clear what to do. So let's use the ratio test. Okay, remember to use the ratio test, we need to look at the absolute value of a sub n plus 1 over the absolute value of a sub n. Fortunately, everything here is positive, so we can stop writing our absolute values. So a sub n plus 1, we have to take this, right? This is a sub n, and we have to plug n plus 1 in here. So that's going to look like 2 to the n plus 1 over n plus 1 factorial. Okay, now divide that by a sub n, which is 2 to the n over n factorial. And ultimately, we will take a limit. But before we take a limit, we should simplify this mess, right? This is really pretty ugly looking. So let's see. This is 2 to the n plus 1 over n plus 1 factorial. And then to divide by this fraction, we can multiply by its reciprocal. So that's n factorial over 2 to the n. And now a lot of nice things happen, right? We have n factors of 2 that cancel here. So in the numerator, we're left with a factor of 2. Let's see, we have an n factorial, and n plus 1 factorial, that's n plus 1 times n factorial. So then the n factorials disappear. So we're left with 2 over n plus 1. And now we can take the limit as n goes to infinity, and we get 0. Right? 0 is definitely less than 1. So the ratio test says that our series converges. In fact, since this limit was 0, it wasn't even a very close thing. This series converges very quickly. Once you get far enough out in the series, this ratio gets very small very fast. Or the individual terms get very small very fast. Okay, so that is an example with the ratio test. I will work out the ratio test example in the handout, which is number 5. I will work that out, but hit pause on this video and try working it out for yourself first. So hit pause. Okay, you worked it out. Let's give it a shot. So here's the example from the handout. Does this series converge? Of course, this is such a mess that we can't use any other tests just because who even knows what any of this is doing. But we can try the ratio test. I think like half of the battle on this one is being careful about taking this expression for a sub n and plugging n plus 1 into it. So when we write a sub n plus 1 over a sub n. Again, I'm not writing the absolute values because everything is positive. So we get n plus 1 squared times, right, if we're plugging in n plus 1, then this stuff in the factorial is n plus 3 factorial over, and then in the denominator, n plus 1 factorial, and then here's 3 times 2 times n plus 1, like that. And now, a sub n, which is n squared times n plus 2 factorial all over n factorial times 3 to the 2n. Okay, now I need to simplify this mess. Again, we're going to take this fraction in our denominator and multiply by the reciprocals, so we get n plus 1 squared times n plus 3 factorial all over n plus 1 factorial times 3 to the, I'm going to multiply out this 2, so this is 3 to the 2n plus 2 times, and now we'll slide this denominator up, taking a reciprocal, so we get n factorial times 3 to the 2n over n squared times n plus 2 factorial. Okay, so what do we get? Let's see, this 3 to the 2n cancels this 3 to the 2n, and so we're left with a 3 squared in our denominator. Okay, this n squared doesn't seem to cancel with anything, so let's just leave this n squared over here. This n plus 1 squared doesn't really seem to cancel with anything, so we'll leave that there. Now here we have an n plus 2 factorial dividing n plus 3 factorial. And those simplify a lot, right? That n plus 3 factorial is n plus 3 times n plus 2 factorial. So when we divide that by n plus 2 factorial, we're just left with n plus 3. So this cancels almost all of this, right? Everything except the last piece, so n plus 3. Okay, and then let's see, this n factorial and this n plus 1 factorial, right? Almost all of that cancels, and we're left with an n plus 1 in the denominator. Okay, now we can take the limit of this as n goes to infinity. So limit as n goes to infinity of n plus 1 squared times n plus 3 over n squared times n plus 1 times 3 squared, which is 9. Let's just write 9. Okay, now this expression is still kind of a mess, but remember, look at it, it's rational, right? We know what to do to take the limit of a rational expression as n goes to infinity. All we need to know is what is the leading term. And if you multiply out the numerator here, you get n cubed for the leading term, plus lower degree stuff, right? And that's because here we have an n that's squared, and here we have another n, so that's going to give us n cubed. In the denominator, our leading term is going to be n squared times n times 9. So it's going to be 9n cubed plus lower degree stuff. And so when we take the limit at infinity, right, we get 1 over 9. Right? And if you don't see why that's true, the trick here is to multiply the numerator and denominator by 1 over n cubed, like this. Right? And when you do that, 1 over 9 pops out. Right? All the lower degree terms, when you distribute this and then take the limit, all these lower degree terms all go to 0. So it's only this first term that really matters. And then when we take the limit, we get 1 over 9. Okay? So what we just found is that the limit of the ratio of an plus 1 to an with absolute values is 1 over 9. That's definitely less than 1. So the series, the original series, converges. Right, so this original series up here converges. You might be thinking to yourself, well, this sort of series is never going to show up. This is the sort of problem that only a math teacher could love. And on the one hand, that's absolutely true. But on the other hand, this kind of messy thing does show up in some physics applications. So one special named function that shows up in solving some important physical differential equations, some important functions are called Bessel functions. And Bessel functions are defined in terms of series like these. And so to even know that such functions exist, you have to know if messy series like this actually converge. And the ratio test is a really important tool to know when functions like this converge. Right? A nice tool for physics is writing things in terms of these kind of series. So having the ratio test around is pretty convenient.